Okay, good morning, everybody. Welcome to the session on thermodynamics and entropy, I think it's called. Quantum information entropy. So that's our overarching topic today. And we are very happy to have Alessandro Pesci here to give the first talk on semi-classical thermodynamics of space-time.
Oh,
Please.
thank you for the introduction. And I would like to thank the organizer for giving me the opportunity to talk about this. And I would try to be impartial, neutral while describing this, but in my talk, the talk will reflect somehow my own path on this topic. And I would like to add the plus there because to semi-classical, because yes, we will consider matter fields, quantum fields of matter, on a classical space-time background geometry. But we will see that there are some hints coming from these considerations towards some quantum description behind for the geometry. So in this sense, something more than semi-classical. Well, let us start from the beginning. These are the celebrated relations which mark the birth of space-time thermodynamics. To black holes, sorry. To black holes, we have to assign an entropy, sorry, a temperature, which is essentially the surface gravity. And this coming from joining the basic tenets of general relativity and quantum mechanics. And this being against all odds from classical considerations. And based on this, we have also that we have to assign an entropy to the black hole, to a black hole, which is given essentially by the area as measured in units of Planck length squared. And notice that all basic constants are here present in this formula. And then the big question we are all aware of is who ordered a statistical meaning to pure geometric quantities which are accompanying GR, like the surface gravity and area. So a step forward in this was the result by Jacobson, who recognized that the field equations are nothing else than the first law of thermodynamics in disguise, because we have here the energy which goes through the horizon, like treated like heat, and we have here the variation of this quantity. Assuming that the entropy is proportional to the area, you get that the Einstein equations are in this form. So, by the way, you recognize here that to this quantity, geometrical quantity, you have to assign a meaning as a heat. No, you see here. Okay, another take on this comes from considering the holographic entropy bound, that you cannot pack more entropy than in a spherical region than the entropy of a black hole, which has as horizon area the area you are considering. Okay. Basically, if you put inside some more entropy, necessarily the area increases. So you cannot do more than this. But this means that if you consider a region and all the physics inside, this can be mapped to degrees of freedom living on the boundary with at most 1 degree of freedom every Planck length squared of area. No? This is the holographic principle. And first instance of this was found in string theory with the ADS safety correspondence, anti-de Sitter conformal field, anti-de Sitter gravitational theory inside, and conformal field theory on the boundary. And further elaboration on this. But we will not focus on this here. Instead, we will consider another formulation which captures the holographic principle in a semi-classical context. And to do this, basically, what we have to do is to consider these conditions here and release them, in the sense that we don't want spherical symmetry and static conditions, but we want generic boundaries and dynamic conditions. And to do this, a first step was the covariant entropy bound, in which you consider a space like two surface and light rays emanating from it orthogonally to it, and in the direction of non-positive expansion, and you follow them. If they go to form a focal point or a caustic, you consider all the region swept by them and the entropy in this region, and you say that the entropy in that region is bounded by a quarter of the area of the two surfaces you started from. This has been further generalized, allowing this null hypersurface to be truncated at a certain point, on a certain surface. And you go to state the bound as follows. You consider a quarter of the difference of the two areas, the starting area minus the end area. And this is the generalized covariant entropy bound. And this is what I consider here in this talk the most general expression of holography, of the holographic principle in a semi-classical context. Now, if we consider entropy of a system as something which is obtained summing over local entropies, you have the pieces, you sum entropy of the pieces, and you have the total entropy. Then it turns out that in an Einstein spacetime, that is a spacetime where Einstein equations hold, you have that the validity, the universal validity of the generalized bound to entropy, you have this if and only if matter satisfies this inequality here. Now, 2 words about this inequality. This inequality means that you are given a thermodynamic system with some values of the thermodynamic potentials. And you imagine like a gas in a room, for example. You imagine to cut a layer of this gas with a physical layer, with physical walls. And while cutting this layer, you are able to maintain, to keep fix the thermodynamic potentials. So this inequality means that you can do this, cutting two layers thinner and thinner, but there is a limit beyond which you cannot go if you insist in keeping the same values of the thermodynamic potential. We can understand this in terms, for example, of the uncertainty principle, in the sense that when you go so thin that you reach, for example, the wavelength of the constituents itself of the system, necessarily you go to change these values. If you want to keep them, you cannot go below the wavelength itself of the constituents. This is what this inequality means. And this L star value here is definitely not the Planck length. You can see this here. There is this factor here that shows you that in general, it is much, much larger than the Planck length. And another thing I want to emphasize is that with all the constants in, you see that you don't have the Newton constant. So this is a flat space-time result. This is something which has nothing to do in principle with gravity. Okay, now we will see some features connected with this inequality that we can call here L star inequality. A first one is that the nature of this inequality is like to be a new law of thermodynamics, of basic thermodynamics. Exactly what happens also for the Bekenstein bound, which is reported here, which indeed was considered as a new law of basic thermodynamics. Here we know is the radius of a spherical surface around the system, which includes the system. But look at the difference in the strength of the two bounds. This bound is much, much stronger than this bound because lambda is much, much smaller in general than R, okay? But I would to emphasize here that this is something local, okay? Flat spacetime physics, local. This is something which arises in flat spacetime physics because also here you see dimensionally the relation is such that also here the Newton constant does not appear, okay? It's something which in principle has nothing to do with gravity, the Bekenstein bound. But as a matter of fact, the intriguing part is that it is just attained, is precisely attained by black holes, this. So this is something which is meant to be applied also in general situations with strong gravity. Instead, this bound here lives only locally. Okay. Now, this L star bound can be attained. It's very simple to attain this. You consider, for example, black body radiation. You have a peak energy. Instead, in terms of this peak energy, you have a wavelength you associated to the photons. You use this wavelength, and you get something like this. The wavelength is related to temperature by this for the photons corresponding to the peak. But in case of a photon gas, the L star is exactly this. So that you reach this L star bound. But this means that if you take a layer of a photon gas so thin as to have a thickness, the wavelength itself of the photons, you are also attaining the generalized entropy bound. And if we pause a moment and think about this, we could ask why this is the case, because in general, one could think that the generalized bound is by far satisfied, not just attainable, no? But you have matter systems that just attain it. Now, another feature coming from that, related to that L star inequality are the relaxation times of thermodynamic systems. In the sense that when you have a thermodynamic system, you put it away from equilibrium, it tends to go again to equilibrium, and it has a characteristic time for going to equilibrium. And this is a known result that using information theory and ordinary second law, you get that there is a bound, a lower bound to this relaxation time, which is given precisely by 1 over pi t. This was found by Hod. And this Hod bound is, you see, this is exactly the expression we met before. So also in this case, we have that the Newton constant is not appearing. So this is something which lives in a space-time, sorry, in a space without gravity, flat space-time. But again, black holes, looking at the ring down modes when a black hole is put away from equilibrium and come back to equilibrium, you have that precisely black holes are able to attain this bound. This is another intriguing aspect of the situation. And what has our L star to do with this? But it's very simple. If you consider our layer of a photon gas, and if you take as speed of propagation the speed of light, and we consider the time to go to equilibrium, the transition, the time it takes to go across the thickness, you have clearly this universal bound. Okay, So this system is able to saturate also this bound, this of the photon gas. But there is also another situation in which this comes about, completely different field. This is the so-called KSS bound, which is about the ratio between viscosity and entropy density. This bound comes from string theory. You have a gravitational theory in the bulk, a thermal theory on the boundary, equivalent to it. Every time you have these two theories equivalent between them, you calculate things and you find inevitably, unavoidably this relation to be exactly this, okay? And in general, you have this. Now, also this is something which has nothing to do with gravity. Look at the constant. And again, this bound is exactly attained by black holes. No? And if we go with our L star through this, we find that this ratio can be written this way, where L is the correlation length of the system, of the thermal system. And since this length cannot be lower than the wavelength itself of the constituents, you have that expressing also the thermal velocity in terms of L star. You have that the bound is by large satisfied by non-relativistic systems. In case of ultra-relativistic systems, if the correlation length can be as low as the wavelength of the constituents, you can saturate, just attain the bound. But to have this L to be equal to the wavelength of the constituents, you need that the radiation field you are describing is strongly coupled, because otherwise the correlation length cannot be so small. And then you get that our photon gas in this case is not able to do the job, but you have to consider not a photon gas, but some, for example, gluon gas, in the sense that you need something strongly coupled. And as a matter of fact, at experiments at colliders, you have that in heavy ion relativistic collisions, you can count the particles as a function of the direction and momentum. And you have this coefficient here, which is a function of the momentum, it's the elliptic flow, which is related to the viscosity over entropy density, and is found to be near to the lower limit. So that this fluid you have, the quark gluon plasma, is with a viscosity as low as possible in this sense. Just it saturates the bound. Now, let us look at things differently. Assume that we don't know of Einstein equations, but we still have the generalized bound. Then if you are given some chunk of matter here, it has some entropy. So you necessarily, if this holds, you have that the area has to shrink. So you have curvature. Okay. So in a sense, you get curvature from entropy. But we have also to pay attention to the fact that to a same mass energy, you can assign very wildly different entropies given that mass energy. So that things are like if gravity fills all the possible degrees of freedom you can associate with a given mass energy. Okay. Another consideration is that regardless if this holographic bound is to be considered primeable or if it comes together with the Einstein equations, you have that it implies that there is a limit length, because to see this, we just consider again our photon gas here with a thickness of the distance between the two layers given by the wavelength of the photons at a certain temperature. Then we increase the temperature. Increasing the temperature, it increases the entropy density. This means that given the way the entropy density depends on the wavelength of the photons, you have a larger curvature here, so that you go to a prime which is smaller, and you go on in this way until you get a limit in which you are in this situation here. And you cannot go beyond this limit, because otherwise the photons cannot be still inside the system. So this puts this limit, putting numbers in, gives a limit of this kind. So what we have seen up to now is that all of this connection between gravity and thermodynamics and quantum information at the end revolves around this fact that there is a limit length. No? Can be understood in this way. And now one would like to insert the existence of the limit length in our metric description of space-time. This can be done in a consistent way, in a sense that it has been done here by these authors. And it has been then extended to include also null separation between events. What you want to have is that the separation, the distance between two events, go in the coincidence limit to some finite limit instead of going to zero, as you would expect, okay? So, and it extended to null intervals between the events here, and also applied to black hole horizon with null generators here. Okay, and the point is that you want to go from a quadratic distance to a new quadratic distance with these properties, with this property. Something which is like impossible to have, because when you go to coincidence, to get a finite limit, you would need the components of the metric tensor, which are diverging, so that you would have something which is diverging at any point of space-time. But point is that we face here something which is non-locality in the smallest scale. So if you use as tool something which is not intrinsically non-local, we could hope to have a handle on this. And this is the case in the sense that, look, using the bitensors, quantities which depend on two space-time points, as, for example, the quadratic distance itself depends on 2 points. We regard x prime, for example, like a fixed point, a base point, and the other as a field point around it, which permits us to have information about the metric properties. And it has been shown that going to require this implies to promote the metric tensor to be a metric bitensor with this form, where A and alpha are scalars, biscalars, and T is the tangent vector to the geodesic connecting the 2 points. And adding also an information, a point regarding causality, in the sense that we want to say something about how information propagates in this new effective spacetime. And what we require is that the 2-point function of the D'Alembertian in the new metric, effective metric, is given by the 2-point function in the ordinary metric, but evaluated at the shifted point. Okay, requiring this, we get that the metric bitensor is uniquely defined, obtained, where A and alpha are given in this way. Delta is the Van-Black determinant, and delta S is the same at the shifted point. Well, here we see that when we go to coincidence, sigma squared goes to 0, and we have something which is divergent. So at any x prime in spacetime, we have something divergent, as we promised before. But thanks to the bistructure, at any fixed x prime, we have the possibility to explore the metric properties of this effective spacetime. Okay, thank you. And looking at dependence on x. And okay, this has been extended to null separations. The problem here is that the distance, the quadratic distance is identically vanishing. And another problem is that when you consider the 2-point function, it is diverging all along a null geodesic. But these two problems can be dealt with, and we go to obtain a same final expression, very similar final expression. And, well, some results one gets with this metric, new effective metric, is that if you look to the Ricci scalar and you express it in this new metric, you get, for example, in the case of null separation, this expression, and where we recognize here the heat of the horizon, okay? So we get for free something which is, you consider the Hilbert, Einstein-Hilbert Lagrangian, the Ricci scalar, and you get for free that the meaning it has in this spacetime with the minimum length is the heat of the horizon. So you have something which is thermodynamics for free, okay? And related to this also, areas shrink to finite values. When you go to, you consider a ball shrinking to x prime, the area does not go to 0, but effectively goes to 4 pi L square in 4 dimension with plus these corrections. Then this can be used to introduce degrees of freedom for gravity, because at the point you have this limit area, you take this as a number of degrees of freedom in units of L squared. You join this with matter, you have the total entropy with this LA playing a role of somehow of momentum, and minimizing respecting to this, you get this equation, which again is the Jacobson result, but now using also some micro degrees of freedom. So you get something, in a sense, something more, because something of a statistical mechanical flavor, a beginning of this. And well, this is also work playing around this thing. I cannot say now with this. And using it on the horizon here is has been done in 2 different ways. Max Fan can explain one of these ways. It's present here, this conference. And going to shrinking the area here, you have x prime. Here is the event of crossing of a chunk of energy across the horizon. And shrinking here, you have a finite limit, so that what you get is that the area of the horizon can vary only by discrete amounts. This gives a cut of energy, below which you cannot have the variation, so you cannot have the absorption of that radiation, of that mode of the radiation. And this gives you something which has to do with coalition black hole events that are studied in gravitational wave. You have 2 black holes which are orbiting around each other, and they emit gravitational radiation. The frequency, or the orbital frequency, increases. The frequency of the gravitational waves is 2 times the orbital frequency of the 2 objects. At the end, they merge. And what is plotted here is that during the inspiral, you go in vertically, starting from some threshold energy for the detection, and you go up the merging, the energy, the frequency corresponding to the merge between the 2 black holes. And what happens is that these gravitational waves emitted are in part absorbed by the black holes themselves to the horizons, okay? So that this is a phenomenon which is called tidal heating. And this tidal heating affects the evolution of the system. So that if your observable is you count the number of rounds of the two objects, the evolution of this with time is different if it is present tidal heating. So what is shown here is that if you take, for example, the limit length to be the Planck length, you go vertically here this way, and you have plotted here the threshold frequency coming from the existence of the limit length for various spin of the black holes. And you see here that all along the in spiral, you are below threshold, so that you completely suppress tidal heating. So this means that if your experiment is so precise that you are sensitive to tidal heating, you are also sensitive to the absence of tidal heating. So you should be able to put in evidence the existence of the limit length. This is one thing I would like to say. So this is another application of this, but I have no time. There is the poster of Max you can look at. And this is my conclusions. I would like to stress only these open problems. Why is true is, it could be very interesting to have a first principle proof of this inequality in flat spacetime, to have a fundamental theory which proves this formally. And why the general covariant entropy bound is attained and not just satisfied by far. We saw before that for the photon gas it can be just attained. But given the importance of the limit length, should any quantum theory of gravity foresee, if not starting from it, the existence of a limit length? And another thing is that should the geometric description, our beloved geometric description of gravity, definitely give way to some description based on statistical correlations? Well, that's all. Thank you for the attention.